The stress on power system engineers can be pretty overwhelming. Consider the demands of electric vehicles. Everyone wants more power, but you have to be more efficient when using it. They want bigger batteries, of course, for longer range, but they also want to spend less time charging those batteries. They want higher voltages and more current, but smaller electronic components that run cooler. It almost seems impossible. Thankfully, TDK is doing some of the difficult work to make the power engineer's job easier with their advancements in Ferrite cores with distributed air gaps. Today's Tech Chat is sponsored by Mouser Electronics. This is where we chat with engineering experts about the latest innovations and the technologies that are shaping and reshaping our world. Today, we will be chatting with Chris Spatafora, the Product Marketing Manager in the Magnetics Business Group at TDK Electronics. Thank you for joining us today, Chris.
Thanks for having me, Dale. It's a pleasure to be here.
So, why don't you give us a little overview of your presentation today?
Okay, so what I'm going to talk today about is a new product that we've introduced a little bit ago, and it's our Ferrite cores with distributed air gaps. And basically, I'll kind of run by why a gap is important, why a distributed gap is important, and the benefits for that gap, and a couple little technical areas as far as the performance and basically, what the product and the technology is all about.
Well, that sounds great. So, let's dive right in.
Okay. So distributed gaps, they've been around for a while, and they really increase the power handling capability of a magnetic component, let's say. And why are they important? Well, they're important for many different reasons. In transformer and choke designs, the ferrite core typically has a pretty large gap in it, and that large gap controls a lot of the magnetic properties in the finished wound magnetic, but that gap does cause some problems, and it's a challenge for designers to address those problems. And the biggest one is the result in the large fringing flux fields and the emitting stray eddy currents that go into the winding area. So, as higher frequency magnetics also contribute to proximity losses, the distributed air gaps will be able to increase the power handling capability and enable the higher currents to pass through the device.
Now, I'm admittedly not an expert in magnetics, so help me understand that figure on the left. Is the flatter green with air gap figure, is that better performance than the red without air gap?
Well, what that allows it to do, it handles more saturation current. So when we look at that's the BH curve, and we look at that curve with the air gap. What it does is it shifts that curve out over to the top on the very top, the BSAT, which allows for more current handling capability. So we talk about saturation, okay? And what does that really mean when we talk about a transformer or choke? Well, the magnetic properties of ferrite cores and other magnetic materials in their assembly have certain characteristics, and one of them is the saturation current level. And what that says is that when the core is excited, meaning current flows through, it can handle so much. Let's say it has an infinite number based on a couple different things. By introducing an air gap to that, we increase the current handling capabilities. So when we look at energy transformation, it can handle more load, it can handle more current before the core saturates and then ceases to exhibit its magnetic properties. It ceases to transform the energy into a usable form.
Oh, that was really helpful. Thanks.
Mhm. So, distributed air gaps, one of their biggest things that they do is they lower fringing flux losses. It's a little complex slide here, but I'm going to kind of break it down for you. So if we look at the slide in the upper left-hand corner with one air gap, we see the profile in the blue area, which is called the winding window. And that winding window is basically where your copper windings go in, or in the case of planar magnetics, the board tracings go in. And that center area is the gap. It's one gap. And you see the large red and multicolor areas emitting from that center area, that center gap. So, like anything else, red is danger. So if we look at the one air gap, we got a lot of red in there. And then if we distribute that gap, and that's a mechanical dimension, if we distribute that into three smaller identical gaps, you see that the fringing flux fields are minimized when we distribute that gap. Here's an example of three non-identical air gaps. They're proportional. The fringing flux that's emitted into the winding area is uh, broken up accordingly. And then if you look at the one on the lower right with five identical air gaps, you're basically eliminating all that fringing flux that's penetrating into the winding area. So you want to think about it this way, the smaller the fringing flux influence in the gap area, it allows for a larger unaffected area in the winding space, let's say. So this really basically lowers the fringing flux by approximately 70%. And that's from a single gap down to three identical air gaps.
And so it would indicate from this the difference between three non-identical and the three identical that controlling your manufacturing tolerance is pretty important as well.
Yes, absolutely. Now, look, there's different ways to get to this, to the different, different gap levels, and some designs might call for a non-identical gap, but again, it's more, let's say, how someone specifies what they need and how then we build it for them.
Okay. And the part number listed at the top for this example, do those numbers 55, 28, 25, do they have any significance?
Sure. So in the realm of let's say ferrite cores, there's standard core geometries and sizes throughout all industries. That represents a typical E core, and we call it an E core because it's shaped like an E. And the size is it's a 55 millimeter by 28 millimeter by 25 millimeter. So again, pretty much industry standard designations there: E55, 28, 25.
Excellent.
So you had asked about the three non-symmetrical gaps, and I touched base on the five gaps on the previous slide. But let's take a look at this. We've done a lot of simulation and a lot of actual hard studies as far as physical measurements. And what we found is the proximity losses decrease as the number of smaller air gaps increase, right? And then one says, okay, well, if that's the case, then give me as many air gaps as you can. Well, at some point in time, one really's got to look at the cost. What does it cost to do this? And what's the sweet spot? And if we look at this chart, we found from an efficiency standpoint, with cost over performance, that three identical air gaps is probably the best value out there when doing one of these designs. If you look at the five air gap chart on the very far right of the graph, you see that you do pick up a little bit more efficiency as far as the performance, but then you have to weigh the cost, right? So the best performance cost ratio is achieved with the three identical air gaps.
Now, you mentioned at the beginning that this is kind of a new product for you. Was there something previously, either in the manufacturability or just the economics of the market, that prevented you from going to three identical air gaps earlier?
Well, distributed air gap and the concept of distributed air gaps has been around for decades, probably literally 30 plus years, right? Um, the big problem back in the day when we did those designs and those builds was there was no real automation or standardized manufacturing process. So when we decided to develop this product line as a standard product line that's available for the masses, we needed to come up with a new way to build the product. In the past, they were all very manually assembled, very manually put together. The batch to batch tolerances were pretty wide. So we at TDK decided and allocated resources to come up with a standardized manufacturing process. And what that entails is that we set up complete, fully automated assembly lines that are very repeatable so that when we make the product and we assemble the product, we're able to control those tolerances from batch to batch production. And in turn, we've been able to actually bring the cost of series production, mass production, down to an acceptable level to the marketplace.
Oh, that makes a lot of sense. Do you think going forward, as you continue to improve your manufacturing processes, Will at some point will five gaps become more cost effective relative to the performance, or do you think three is kind of here to stay for a long time?
Well, there's a couple different areas of cost benefit analysis that we have to look at. So each time we do an assembly, like in any manufacturing process, we have a thing called stack tolerances, right?
Hmm.
So as we start to add tolerances to these different gaps, so when we create a gap, it has a certain tolerance. Then when we create three gaps, those tolerances are then stacked by three. And when you
Right.
create five gaps, then those tolerances then start to go up exponentially again. So, and when we talk about tolerance, we talk about the electrical tolerance of the final AL value. So, one of the benefits of our product is that we're able to offer the complete line with a standard AL value tolerance of plus or minus 10%, which in the realm of things, when you look at it, is pretty incredible for what's being done.
Well, that makes a lot of sense to me.
Okay, so let's talk about performance and actual performance here. Um, you're looking at actual thermal image tests right here, and we're going to compare um, two frequency levels, and this is important as we get it further into the discussion. So, we measure the performance of a transformer choke at different frequencies, and if we look at this first gap at 50 kilohertz and one gap at 200 kilohertz, we can actually see the thermal imaging of this particular build. So this is built on a standard industry standard core, an ETD family core, the ETD 29 series, and their actual, test comparisons. And then we look at the same product, the same build, the same number of turns, the same bobbin, the same winding configuration, but if we swap out the cores and put in a distributed gap core, look at the difference. It's night and day as far as the thermal imaging is concerned, especially when you at the 50 kilohertz level and the 200 kilohertz level. Um, significant savings as far as heat is concerned. Now, with any wound magnetic, heat equals losses, and losses equal inefficiencies. So this is a real big important factor to consider of how well your product, your N well magnetic performs in a circuit.
And I would assume, as with most electronics devices, that lower heat means you can operate at higher ambient temperatures and also improves the reliability.
Exactly.
So, are there other benefits related to the improved thermal performance provided by these ferrite cores with air gaps?
Yes, there are. There's a couple of them, and this one's pretty significant as well too. We actually stumbled across this data after reams and reams of data points and analysis and testing. So when we start to look at high frequency magnetic designs, right? Usually, typically, those designs are achieved using what we call high frequency Litz wire, right? So as the frequency goes up, the need for Litz wire increases. And what we found, due to the temperature rise reduction, um, the distributed air gap configuration versus a solid wire distributed gap over a high frequency Litz wire design actually reaches better performance with a better RDC. So this is a lot going on in this chart here, but we look from the left to the right at 50 kilohertz, the difference is not that great. But if we start to move the frequency up into that 200 kilohertz and above level, where a lot of people like to use Litz wire, you can see that the high frequency lifts one gap and the high frequency lifts three gaps compared to the single wire and the three with one gap and three gaps. The spread as far as their performance in the power handling capability is very significant. So, at the end of the day, when we look at this, we say, well, in some cases, there's a good possibility that somebody could actually use a solid wire in place of a high frequency Litz wire. And where that comes into play is the actual overall cost of ownership of this finished magnetic device, since high frequency Litz wire is extremely expensive compared to solid wire.
And Litz wire, is that just a bundle of small wires together?
Yeah, there's different types of Litz wire on the market, and very good product out there for many applications. It's a nesting of very thin strands, and one would specify the number of strands and the number of bundle, for the particular gauge of wire that they're trying to use for any particular application. And again, it's something that we came across over analyzing all the data. We talked a little bit in the beginning about standards, and what's so great about this product is that it's accessible to the masses via distribution. We developed a series of products in standard cores that the industry uses every single day. We developed a list of standard AL values, that's the electrical value, that the core family will support. And as you can see here, we offer them in E cores, ETD cores, PQ cores. We also offer them in many other core configurations and materials as well. The process itself lends itself to be able to be incorporated in almost any core geometry or family and size, and almost any given material offering in our portfolio.
Well, that provides a lot of different options. Then, as you noted, there's some standards here, and so basically, go to the shelf and you've got a solution for people.
Yeah, and again, we offer a range of standard family product. Let's say, for instance, somebody's working with a PQ core, they need a smaller PQ or a bigger PQ core. They might want a different AL value from our standard. That all can be achieved, but the availability of something to get your design started is key. So we also offer a wide range of tools for the customer. The step files are available on all the standard ranges of the distributed gap cores, and we also offer all of the accessories to go into all the core sizes. So you can go straight to the distributor, off the shelf, core, bobbin, and you're ready to go start your design.
Yeah, that's a much quicker way for people to get started. If you've got all the files to drop into their board design and then they can just order these parts off the shelf, it's going to streamline that production and improve their ability to get product in the market.
Yeah, and it's nice to have everything available at one place. Really does enhance your time to market with your design. And again, like I said earlier, a lot of times in the past this was all custom stuff, and custom stuff takes time. The fact that you can go right into a full-blown design very quickly really improves your time to market, and time to market means you're going to capture and win more business.
Exactly right.
Some of the benefits, this is kind of a little bit of a recap to what we already talked about, but it's important to note that our distributed air gaps reduce the proximity losses by about 70%. That's that whole interface with the winding window and the winding area. It also enables the use of the larger winding area by reducing that fringing flux. And what that means is that the designer can pack more copper into that winding window that they have to work with. It also improves the thermal performance of a solid wire design, but also high frequency Litz wire designs. And there's the possibility to enable a core size reduction by one class thanks to that lower lining loss. So example, we talked about that E55 core. So maybe a design started out with an E65 core based on the core parameters and the winding requirements. But through the better use of that winding window and that improved thermal performance, possibly the designer can now drop down to the next size class to maybe an E55 core. And that's a huge cost savings in the end result. Another example, an ETD 59 can drop down possibly to an ETD 54. So there's other significantly increased power density options as well out there too. So there's quite a big benefit package to designing with distributed air gaps.
Well, and more power and a smaller footprint seems to be the common thread across nearly every aspect of the electronics industry today. And that requires continual innovation, which is great news for our electrical engineering audience. It's new design challenges and new opportunities.
Yeah, absolutely. Absolutely.
So, with those benefits in mind, what are some key applications that can really benefit from these ferrite cores with distributed air gaps?
So one of the biggest areas that we focus on is automotive and industrial products. So when we talk about size reduction, weight reduction, and improved thermal performance, onboard chargers, DC to DC converters for XEV, that's the trend, right? We need to make them smaller, they need to handle better power handling capability, and they need to be cooler. So perfect target market applications for those areas. Now, segueing from that is the charging station. And it's not just EV charging stations, it's big material handling charging stations. Anywhere where you're looking at that big, chunky magnetics with a big gap. These are perfect applications. And of course, let's move on into the industrial side of this slide. Solar inverters, any UPS, and any industrial switch mode power supply are perfect candidates for a distributed gap product when we look at the overall design of these magnetics.
And so these applications include several of what we're seeing as the hottest topics in the electronics world today. That's EVs, renewable energy sources, and then the power supplies that help compensate for those inconsistent renewable energy sources.
Exactly. Exactly. And as we see the electrification of so many industries, the demand on the magnetics for smaller, lighter, more efficient magnetics in these growth markets is evident all around us.
Yeah, that's exactly right. Thank you, Chris, for that great technical introduction to distributed air gap ferrite cores.
You're welcome. It's a pleasure to speak with you today.
If you're looking for more information, head over to Mouser Electronics, where you can find more technical details and purchase products from TDK. And join us again next time on Tech Chat, where we chat with leading technical experts like Chris and the electronics companies like TDK that are improving our world every day.